All right, we're in unit number 5, example number 6, page 11. And we're going to do an example that not real hard, but it's going to pull together some of the concepts that we've been working with in the past couple videos. So let's read the opening statement first, and then we'll do our free body diagrams. So here's our opening statement. It says a 2-kilogram box is pushed across the floor from rest. Now it's going to be important in just a moment. From rest with a constant horizontal force of 10 newtons for a distance of 2 meters, no friction. All right, so, and well, you see I've kind of done some of this already, but we'll work it out. So here's my box. We know that there's some weight. We know there's a normal force. And we also know that somebody's pushing on it with a force of 10 newtons. We know that for sure. And we're going to assume that the box moves to the right. So this is going to be, that's going to be displacement. It's not an arrow for this diagram in terms of a force, but I need to at least show you which way the box is moving. It's moving to the right. You would probably already assume that, but that's cool. All right, so question B says, or part B says, how much work is done on the box by the 10 Newton force? Well, we know that work is equal to force times distance times cosine theta, or F dot D. And if we want the work done by this 10 Newton force, then I have to plug 10 newtons in as the force. And then I want this D. This D is going to be basically how far it moves. And if we go back up here, that's 2 meters. And then cosine of, now we got to do this angle. So here's the force, and there's the movement, and the angle between those two is going to be 0. And let's plug that all into the calculator. It's going to give us 20, but we'll do it just so you can see it. There it is, 20. And since this is work, that'll be 20 joules. So how much work was done by the 10 Newton force? 20 joules. All right, letter C. What is the change in kinetic energy of the box? Well, to get this, we kind of have to remember what we talked about in the previous video. The previous video said, anytime we do work, that's equal to a change in kinetic energy. Let me write that down so you can see it. Anytime we do work, that's equal to a change in kinetic energy. Well, if I want the change in kinetic energy, which is this guy, then I need to know this. Well, what is that? That's the 20 joules. So by substituting that in, I can say that I did 20 joules of work, and that 20 joules of work caused a change in kinetic energy of 20 joules as well. All right, part D. What's the initial kinetic energy? Well, to get the initial kinetic energy, I got to go back up to the beginning. And remember this? They told us it started from rest. And if it starts from rest, then our initial kinetic energy is going to be 0 joules. All right, part E. What is the final kinetic energy? Well, this requires requires you to recall what change in kinetic energy is. Remember, change in kinetic energy, yeah, it's equal to work. We did that here, but it's also, I mean, you can unpack that and say a change in kinetic energy is equal to final kinetic energy minus initial kinetic energy. And we're going to use that because I know that the initial kinetic energy is 0. I know that because we just said that right here. And if they want the final kinetic energy, well, then that's going to be equal to whatever the change was, assuming this was 0. Well, the change was 20. That came from up there. So 20 joules is equal to our final energy. All right, next question. Next question says, what is the final velocity of the box? Well, I just figured out what the final kinetic energy is. And I know that in the equation for kinetic energy, I have speed in there. And that's the speed, that's the final speed, because this will be the final kinetic energy. So I'm going to solve for this. So I'll go plus and minus square root 2ke over m. and then sub numbers in, so VF is equal to plus or minus the square root of 2 times the kinetic energy. All right, what was that? So I'll go back here. Kinetic energy was 20 joules. Party. So we'll go 20 joules here. Over the mass. Let's go back to the, I think in the very beginning they gave us the mass. Yeah, here it is right here. Mass is right there. So we'll just plug in 2 kilograms. And the final speed is equal to, let's plug all that in. Can I squeeze it in there? There we go. Alright, what I usually do on this is I'll figure out all the stuff on the inside and then I'll take the square root at the end. So 2 times 20 divided by 2, get that. And then I take the square root of that answer. And there it is, 4.47. Alright, part G. How much work would be needed to bring the box to rest? Okay, let's see if we can work this out. We know work is equal to a change in kinetic energy, which is equal to kinetic energy final minus kinetic energy initial. We didn't start with, we're coming to rest. So if we're coming to rest, that means our final is 0. What was our initial? Well, our initial would be the final from the first part. So how much kinetic energy do we have at the beginning? Well, if I just kind of slide this down a little bit, we had 20 joules right there. So I'm going to go minus 20 joules. So the work needed to bring it to rest is negative 20. Why negative? Remember, when we're dealing with work, that negative doesn't tell you, it's not a vector question. It's not a direction. It indicates what's happening to the energy. Is energy going into the system, or is the energy coming out of the system? And in this case, if it's negative, it's coming out of the system. It's causing the object to slow down. And that would make sense. So, because if you're bringing it to rest, then it's slowing down. All right, letter H. How much work will be needed to bring the box to rest if the box was traveling at twice the speed? And then how much further will it take the box to get to rest? Alright, this one's a little bit more involved. So let's see what happens here. We're going to start with the work kinetic energy theorem. I'm going to blow this one up. So I got work is equal to, when I say blow it up, I'm just talking about just expanding that equation. I know change is going to be final minus initial, so by blowing it up, I'm just going to expand that a little bit. All right, now we're bringing this box to rest. That means our final kinetic energy is 0. All right, now we want to know how much work. To get work, I have to do kinetic energy. And so I'm going to go ahead and substitute the equation in. So minus 1/2 mvo squared. Move it up here, 1/2. All right, 1/2, negative 1/2. Now, m. We don't know what m is right now. I'm just going to kind of imagine I don't know it. I'm going to do it kind of algebraically here. And then look at what it said here. It says it's traveling at twice the speed. So instead of saying plain v, I'm going to say 2v. But that 2 goes inside the parenthesis because that squared, this 2 squares not just the v, but it squares everything that v is. And since we're squaring the speed, since we're doubling the speed, I have to square that 2 as well. Now look what happens here. If I multiply this right-hand side by 2, but I square that 2, that really has the same effect as multiplying by 4. Let me show you a couple steps and see if I can argue that for you. So we're going to do m, do 4 times v squared. There's the 4 because 2 squared is 4. I'm going to move this 4 way out here now. So 4 times negative 1/2 mvo squared. Notice that this right here is my kinetic energy. That means I've multiplied it by 4. And if I multiply this side by 4, When I multiply this by 2, it's really multiplying everything by 4. So the question, how much more work will be needed? Well, 4 times that work. 4 times that work. The next question would be how much further? Well, how much further? We know that, let's see if I can go one step further. Work is equal to FD cosine theta. So I could almost imagine multiplying that distance by 4. So the idea on this question is this. If you double your speed, because that speed is squared, that has a dramatic effect on the amount of work that you're going to do and also how far that object is going to go. And the great question in letter I, the great follow-up on this is, how should your answer in letter H affect the way you drive? Well, look at what's going on here. If you double your speed on the highway, here's your double the speed. What's that going to do to your stopping distance? Your stopping distance is going to be not doubled, but it's going to be quadrupled. It's going to be 4 times the distance. So just a little increase in speed on the highway gives you a dramatic increase in the stopping distance of your car. So it's going to multiply the stopping. Let's see. Well, how should you do? It should cause you, knowing that, to hopefully to slow down, because it's going to really affect your stopping distance. Okay, our next video will be example number 7, and I think example number 7, yeah, it's going to be our last video for this chapter. We'll see you in a bit.